this particular integral involving the Riemann-Xi function. Now, if you look at the function, the integral that I had on the previous slide, this was the exact one, with regards to which Hardy was saying that this can be used to obtain the second moment of the Riemann zeta function. So, so a lot of connections between these integrals of Riemann-Xi functions. Now, let me go over a brief definition of modular relation. I have intentionally made it vague so that we can incorporate many results. So if you look at modular forms, these are nice functions defined in the upper half plane that transform nicely both under this inversion as well as translation. However, by a modular relation or a modular type transformation, we mean a relation which is governed only by the inversion, but not necessarily by translation. Equivalently, as I have said before, we can also conceive a modular relation to be a one which is governed by this transformation, alpha going into beta, where alpha beta is 1. So Ramanujan's two transformations that we have discussed, they are all of this form. F of alpha is f of beta. And a generalized modular relation is a one which may involve additional variables besides alpha and beta. Sorry, I have written here Z. I meant alpha and beta. So one question that arose in my mind back during my PhD days is that Ramanujan has this more general integral in his published paper. So isn't there a modular type transformation associated with this general integral? And I worked on it and I found out this formula. So now here this phi function is defined here. Phi of z comma x is constructed by means of this Hurwitz zeta function. So you have zeta of z plus 1 comma x. And again, if you look at its asymptotic expansion as extends to infinity, then you subtract from it the first two terms in that asymptotic expansion, and thereby you get something which is big O of 1 by x squared, of course the implied constant depending on z, and you can construct a series of it. So this is one result which I found, and this will keep on coming in the next part of the talk, but I would not say anything more about this formula now. Because Hurwitz zeta function is appearing in this formula, let me briefly go over the basic properties of the Hurwitz zeta function. So everyone knows that zeta of s comma a is given by this absolutely convergent series for real part of s greater than 1, summation 1 upon n plus a to the s. When a is 1 and when the real part of s is greater than 1, it is trivial to see that the Hurwitz zeta function reduces to zeta of s. Actually, this is true for all complex s, but let us not go into how to prove that now. But for real s greater than 1, it is trivial. Let me assume that a is strictly between 0 and 1, and a is not equal to 1/2. The reason I am omitting a equal to 1 and a equal to 1/2 is because in those special cases, the Hurwitz zeta function reduces essentially to the Riemann zeta function. So then there is no new object. What we did going from the Riemann zeta function to Hurwitz zeta function is just a translation of n by a. But that actually destroys many of the properties that Riemann zeta function satisfies. For example, unlike zeta of s comma a has no Euler product. Davenport and Heilbronn have proved that when a is rational or transcendental, and Cassels has proved in the case when a is algebraic irrational that zeta of s comma a has infinitely many zeros in real s greater than 1. Note that that is not the case in the case of Riemann zeta function, because from the infinite product representation or the Euler product representation, one can actually show that zeta of s does not vanish in real s greater than 1. Also, for a rational, Voronin, and for a transcendental, Gonek, in his PhD thesis, has proved that zeta of s comma a has infinitely many zeros in this strip, which is half of the critical strip. So an analog of Riemann hypothesis is false. There is this beautiful formula due to Hurwitz For real s less than 0, zeta of s comma a can be expressed in terms of what one could call as cosine and sine Dirichlet series. Here I'm assuming a between 0 and 1, and a can take the value 1. But if a is not allowed to take value 1, then I can extend this formula up to real s less than 1 instead of real s less than 0. For a equal to 1, at least in the case when real s less than 0, one can see that this reduces to the functional equation of the Riemann, not the symmetric version, but the asymmetric version. Because this series just vanishes, and here you get the Riemann zeta function. Okay, so that's basically the background regarding Hurwitz's zeta function. Now, one other question is, why are we interested in studying integrals of Riemann Xi function? I have already shown you some nice formulas, some quotes of Hardy where these are useful in the theory of the Riemann zeta function, but there is more to it. So let's go over it first. So Hardy has said that any new formula for Xi of t is of great importance because it may have some connection with Riemann hypothesis, RH. So this very first formula that I started my talk with, or very first integral, remember x there was 1/2 log alpha. So let us put it as x. F was of this form. And now if I take this phi function to be identically equal to 1, then this integral becomes this, and it can be evaluated to be equal to this. One can invoke the theory of Mellin transforms to get to this expression. Note that this is a very rapidly convergent series. Now, if you use Fourier inversion, then you can express Xi of t in terms of Fourier cosine transform of this particular infinite series. Okay, so now I'm going to use a notation for this particular series. Let h sub 0 be 1/8 times Xi of z by 2. And now I'm allowing z to be a complex number. And I'm using that particular series to be phi of u. It's essentially the same series. I have just replaced u by minus u, but this is an even function of u, as can be proved using Poisson summation. So this h sub 0 of z is nothing but this integral of phi of u times cosine z u du. So this is the formula on the previous slide that I just showed you, the one that we get from Fourier inversion. This is the one. Rewritten. Now let us do one thing. In the integrand, let us insert this function e to the power v u square. So when v is equal to 0, then that is just h sub 0 of z. In general, I call it as h sub v of z, and v is a real number. So De Bruijn had considered these integrals, and Polya actually showed that h sub v has purely real zeros, meaning all zeros of it are real. If it is the case that if we have all real zeros for some v, then h sub v dash has purely real zeros for all v dash greater than v. This is the result of Polya. What De Bruijn showed was the zeros of h sub v are purely real for v greater than or equal to 1/2. Note that if this was true for v greater than or equal to 0, then we could put v as 0 here, and so we would get this. And what is this saying? If h sub 0 had all zeros real for real value of z, then that actually proves Riemann hypothesis. How is that the case? You see, in the definition of this Xi was in terms of this small Xi function, which had this functional equation part and some normalization factor. But none of the other factors except zeta vanish on the critical line. And so if this is vanishing on the if this is vanishing for z real, that means zeta is vanishing on the critical line. So if this has all real zeros, then that means the zeta function has, all of the zeros of the zeta function lie on the critical line. And so that proves the Riemann hypothesis. So this was quite close, but not quite, if you want to say from another perspective. So De Bruijn showed that zeros of h sub v are purely real for v greater than or equal to 1/2. As I said, RH is equivalent to this fact that for z real, all zeros of h0 of z are real. Further, Newman showed that there exists a constant lambda between -infinity and 1/2 with the property that h sub v has purely real zeros if and only if v is greater than or equal to lambda. So it's strengthening the results of De Bruijn. So from what I have just said, RH will hold provided lambda is less than or equal to 0. But what Tao and Rogers have proved very recently, that lambda is greater than or equal to 0. So the Riemann hypothesis will be true now only if lambda is equal to 0. And so they say that if RH is true, it is only barely so. Okay, because one doesn't have much room for this lambda. It has to be equal to 0. Anyway, so what I intended to say in these two slides is that these integrals of Riemann-Xi functions are quite important, because suppose you have a Fourier cosine transform of this along with certain other function in here, you can apply Fourier inversion and get new representations for this Xi function, and you have already seen that this particular expression is tightly related to the Riemann hypothesis. So there is another good reason to study such integral. Let us now concentrate on this particular integral of Riemann-Xi function, which was studied by Hardy. Hardy evaluated it to be equal to this left-hand side. And then again, one can play the same game, replace alpha by beta, and you get this modular type transformation. In fact, this is a well-known result. It's called as the Theta transformation. And Hardy used both these equalities to show that infinitely many zeros of the Riemann zeta function lie on the critical line. So that was the first such result of its kind. There is also a generalization of this theta transformation, which is involving one more parameter. One knows it more commonly as Jacobi's imaginary transformation. But let me rephrase it in an equivalent form. But before doing so, I would like to define what we mean by confluent hypergeometric function. So 1f1 of ACZ is given by this series, where these are called as Pochhammer symbol or rising factorial. It's defined by a plus 1, so on up to a plus n minus 1, or one can also write it as quotient of gamma functions. So this is an entire function of z. Here is an equivalent version of Jacobi's imaginary transformation. So you can see how beautiful this formula is. Going from here to here, you are replacing not only alpha by beta, where alpha beta is equal to 1, but you are also replacing w by iw everywhere. And that's the reason why this cosine becomes cosine hyperbolic. So one can say that this transformation takes the form f of w comma alpha is f of iw comma beta, where alpha beta is 1. This formula was known since Jacobi's time. I mean, it's first formulated by Jacobi and proved by Jacobi. But an integral involving the Riemann-Xi function equivalent to these two expressions was not known before. And I tried to find one, and here is one that one gets. So this part was similar to that in Hardy's formula. Hardy's formula involved cosine function here. Now what you get is essentially it's a combination of 1f1s. So here rho of x comma w comma s is consisting of this 1f1, and then you have rho of x comma w comma 1 minus s. So let us look what happens when w equal to 0. So this 1f1 just becomes 1. This exponential becomes 1. And note that here you are evaluating this del function at 1 plus it by 2. So here you will get x to the minus it by 2. And similarly from here you'll get x to the it by 2. So that actually gives you a cosine. So w equal to 0 reduces to Hardy's formula. Now what is an application of such a result? One Well, one can actually extend or give a far-reaching generalization of Hardy's result. So here is the one that we found recently. So I consider Cj's to be a sequence of real numbers such that summation mod Cj is convergent. Lambda j is a bounded sequence of distinct real numbers such that it attains its bounds. And let D denote this region. I'll show you the region in the next paragraph, next slide. And for any W in this region, if I construct this function f sub W of s to be this infinite series, then it also has infinitely many zeros on the critical line. Now, Hardy's theorem is but one special case of this when all but one of your Cj's equals 0, and the remaining one, which is non-zero, equals 1. And when one takes W also equal to 0, then one gets essentially the Riemann zeta function. And so there one gets Hardy's result. Okay, so we have already seen a lot of applications of this modular type transformations involving Riemann C functions. So yeah, here is the region. So previously in Hardy's case, one knew this result only when all but one Cj's were 0 and when W was equal to 0. Then in a work with Arindam and Nicholas Robles and Zarescu, we showed that it is true for W equal to 0, and now we have extended it in this region. Okay, let me discuss one more terminology. What do we mean by modular relation with a theta structure? So it is the one in which the associated function, say f of W comma alpha, will become invariant only when we simultaneously replace alpha by beta and W by IW, as in the case of the theta transformation. So this is the prototype. The general theta transformation is a prototype of a modular relation with a theta structure on it. So theta structure will always mean W going into IW. So let us look at one transformation that I already discussed with you, the one involving Hurwitz zeta function. So this is a generalized modular relation where you have alpha going into beta, but you don't have W going into IW, but you have Z, which remains as Z everywhere throughout. So the question that we asked ourselves was, does there exist a more general transformation of this kind where one also has theta structure on it? So where there would be an extra parameter W, and so there will be a general function here with an extra parameter W, and when W goes to IW, here you get an invariance. So that's the question. Can one superimpose theta structure on the above modular relation? Now, why one would want to do that? So let us first go with this one reason why one may want to do it, because one can get new Jacobi forms from this example. What is a Jacobi form? So loosely speaking, a Jacobi form is a function of two variables. So from H cross H to C, where H is the upper half plane, where one has modularity in the first variable and ellipticity in the second variable. So such a superimposition worked successfully in the case of Ramanujan-Guinan formula. I'll explain on the next slide what a Ramanujan-Guinan formula is, but it is something which is equivalent to the functional equation of non-holomorphic Eisenstein series on the full modular group. Let me define sigma sub minus z of n as sum of d to the minus z, where d runs over all divisors of n. Here is the beautiful formula due to Ramanujan, which was later rediscovered by Guinan. Here k is the modified Bessel function of the second kind, which is defined in this way in terms of the modified Bessel function of the first kind, which in turn is defined in terms of the J Bessel function or the Bessel function of the first kind. Okay, so in order to get this generalization of Ramanujan-Guinan formula, which I have not discussed here because it will be a digression, but the underlying theory that we needed was to construct theory of functions which are reciprocal in this particular kernel. Here you see all three of the four Bessel functions, J, K, and Y. The M function is in terms of K and Y Bessel function. And in order to obtain such a transformation, we also needed a generalization of a modified Bessel function with an extra parameter W. So we developed its theory. So let me explain by means of this flow chart. Here is the Ramanujan-Green formula. It involves alpha and Z, two parameters. I say only two because beta is 1 by alpha. When Z is equal to 0, it's well known as a formula due to NS Koshlyakov. F of alpha is F of beta. And what we did in our work was to superimpose theta structure on it. So we got a formula of this kind. Now, if you look at Ramanujan's formula from the Lost Notebook, it is of this kind, similar to Koshlyakov's formula. So the type is same. I was able to extend it with one more variable, Z. Now, one natural question is, can one incorporate theta structure in it so as to get this result, a result of this form? So before I discuss that result, I would like to go over some definitions. You can choose to ignore these definitions for now. Basically, this delta 2 has a similar construction to what I showed you before in terms of rows, but now I'm having omegas. So these omegas are defined in terms of products of confluent hypergeometric functions. And Humer's transformation between 1f1s is used throughout this work. So using it, one can see that this delta 2 function is invariant under alpha replaced by beta and W replaced by IW. So this is one crucial fact that we will be using. And when one puts W equal to 0, then this simply reduces to the cosine function because, of course, you see these 1f1s just reduce to 1. Let me define this A sub W of Z to be essentially this product of 1f1s. This can also be written in terms of error functions, which I'll probably do later. Okay, so here is the main result. Here is the generalized modular relation with theta structure on it. So alpha beta, as usual, have product 1. W is any complex number. Real Z is between -1 and 1. I'll come back to this definition in a moment, but before that, look at this modular relation. Alpha goes to beta, Z remains as it is, and W goes to IW everywhere. And here is this integral involving the Riemann-Xi function, where you have this delta 2 function that I defined on the previous slide. But now the main point of interest is, what is this function, phi sub W? So I'm defining it in terms of this particular thing, but what is this zeta sub W of Z plus 1 comma X plus 1? This looks to be a new function, and that itself is the main purpose of writing our paper. The reason is we actually stumbled upon a interesting new generalization of Hurwitz zeta function. We call it as zeta sub W of S comma A. I'm going to put up the definition now, but let me warn you that initially when you take a look at it, it may look intimidating, but I'll try to convince you that it's a beautiful function satisfying a nice theory. So what I'm going to do is, I'm going to omit certain values of A. What are the values of A that I'm omitting? Essentially those which are in the set B. So B is all those complex numbers on real A equal to 1, such that imaginary part of A is not equal to 0. So if you see, I'm not omitting A equal to 1, but everything else on that real line, everything else on the line real A equal to 1. Then W is in C minus 0, and let real S be greater than 1. Then our generalized Hurwitz zeta function is given by this infinite series. So as I said, this looks somewhat complicated in the first glance because you have summation of two double integrals, and then you have elementary functions here. One thing that I would like to emphasize is that we have not created this function artificially. It arose naturally when we were trying to generalize a modular relation, the one that I showed you, the modular relation with the theta structure, when we were trying to obtain it, this actually came up naturally. So the summand can be easily shown to be big O of n to the minus real part of s as n tends to infinity. So for real s greater than 1, one can actually guess that this is an absolutely convergent series as before. But not only that, it is also an analytic function. So that I'll say on the next slide. But what I want to emphasize here is that w equal to 0, if you see from here, is actually a removable singularity. Okay, so one can actually have this definition for all complex w. Also, this generalized Hurwitz zeta function has one property which was absent in that of the Riemann zeta function as well as in the case of Hurwitz zeta function. And what is it? Of course, in the Riemann zeta function, there was no A, but in the Hurwitz zeta function, there is an A. But there is no symmetry along real A equal to 1. In this particular zeta function, we very nicely get a symmetry along real A equal to 1. And you can see it's trivial to prove from the definition itself. You replace this A by 2 minus A, you get back the same function. So this is the first of its kind generalization which has symmetry in A besides other possible symmetries which we'll try to find. Okay, before I discuss further properties of this zeta sub w s comma a, if there are any questions, I would like to take them now, or maybe we can take it at the end of the talk as well. Right? Either way, should I go ahead?
So this generalized Hurwitz function, Hurwitz zeta function, does it reduce to the Hurwitz zeta function for some special values?
No, it reduces when w is equal to 0. So that's on the next slide. I'll discuss. Yeah. Right. So yeah, let me discuss that part. So zeta sub w is given by this series, as we have seen. Let us first look at what happens when a is equal to 1. So that reduces essentially to the Riemann zeta function. I said essentially because there is this 1f1 which also depends on s. But essentially, this is a well-known function. I mean, one knows all properties of these two functions. So one can actually get analytic continuation for all c minus 1, for all s in c minus 1, just from the fact that zeta of s can be analytically continued. And 1f1 is an entire function in the first variable, and hence in s. Okay, so from now onwards, we are going to always assume that a is not equal to 1. So, as I said previously, one can show easily using Weierstrass's theorem on analytic functions that this generalized Hurwitz zeta function is analytic in the real part of s greater than 1. Now, here is an integral evaluation that one can actually do. It requires some formulas in the theory of hypergeometric functions, but one can actually deduce this. And you see, there is no sine or sine hyperbolic, and there is no w square. If I go back, there is sine wv, sine hyperbolic wu upon w square. So I'm essentially putting w equal to 0, or you may say w tends to 0. So in order to get this. And then, as I was asked, this reduces essentially to the Hurwitz zeta function when real part of a is greater than 1, and then to Hurwitz zeta function, but with a replaced by 2 minus a if real a is less than 1. So in this sense, we have this generalized Hurwitz zeta function. Now let j sub nu of s denote the Bessel function of the first kind. See, whenever we have a new zeta function, if you work only with real s greater than 1, this is not going to be interesting. One should try to see if there is analytic continuation beyond the right half plane, real s greater than 1, I mean to the left of it. And so once we encountered this new zeta function, our next job was to try to obtain all of its properties that we are able to. So this is one of the main ones. So this zeta sub w of s comma a can be analytically continued to real part of s greater than -1, except for a simple pole at s is equal to 1. But now see what the residue is. The residue itself is essentially a square of 1f1. And when you put w equal to 0, so that you get Hurwitz zeta function, this just becomes 1, and which is a well-known result, right? The Hurwitz zeta function has a pole at s is equal to 1, a simple pole with residue 1. But in this case, the residue itself is this exponential times square of 1f1. So this is how it looks. Zeta sub around s is equal to 1. This thing involving error function is nothing but equivalent to this, equal to this. And then there is this generalized digamma function which we encounter. Now, let me first define this digamma function. We know that psi of a, the usual digamma function, is defined as a logarithmic derivative of gamma function, or one can also have various integral representations. So this generalization comes through the integral representation. We don't know yet what the generalized gamma function is in this perspective. So this is the only definition of psi sub w of a that we could get, or this is the representation that we could get, which we called as the definition of psi sub w of a. Okay, so in other words, again, this is the behavior of the zeta sub w s comma a near s is equal to 1. Now, one reason, one thing that one may feel, why real s greater than -1? Why not all complex numbers except s is equal to 1? Over the period of last 6 months, we were trying to extend it to the left of real s greater than -1, but we could not. So we tried various different ways. So that's open for everyone to see whether one can analytically continue it. Of course, for w equal to 0, because it's the Hurwitz zeta function, one knows that it has analytic continuation in c minus 1. But I'm saying in general. So let me look at one, let me give an example of one paper in electrical engineering that appeared in 2017. The author of this paper says that whenever one encounters square of a confluent hypergeometric function, then one has to resort to approximations and not work with exact formulas. So with the usual, I mean, just the first power of 1f1, it might be possible to work with exact results, but when one encounters 1f1 square, generally in physical problems, one has to resort to approximations. Even though the confluent hypergeometric function which this person encounters is different from what we have, I just wanted to show that here is one way how one may study a square of 1f1, this particular 1f1, and that is through its representation as limit of s minus 1 times this generalized Hurwitz zeta function. So when one has more and more theory of this function developed, that may be utilized towards working with problems which involve squares of confluent hypergeometric functions. At this particular time, it is with respect to this particular one, but I'm saying subsequently more general functions one may be able to consider. Okay, so I think I'll very briefly go over this. So psi sub w of a again satisfies this symmetry along real a equal to 1, which was not the case in the case of the usual digamma function. When w equal to 0, you get the digamma function, as in the case of the zeta sub w reducing to zeta of s comma a. So here is the integral representation for digamma function that I was talking about. So one special value is psi sub w of 1 is this particular expression involving the error function. Psi of 1 is minus gamma, as one knows. So when one puts w equal to 0 or w tends to 0, this is again a removable singularity. So this particular function becomes just 1. Okay, I would like to build upon some more properties of this zeta function. So if one looks at Hurwitz zeta function, then this is a well-known result of Hermite. Why is this an important result? It is because it at once gives you analytic continuation in C minus 1. How? You of course see a simple pole at s is equal to 1 here, but then this integral is an entire function of s. This is also an entire function of s. And so you get at once this analytic continuation in whole complex plane except for s is equal to 1. So that's one of the striking features of this formula. So naturally, because our first goal when we encountered this new zeta function was to try to analytically continue it beyond real s greater than 1, we decided to approach it through a generalization of Hermite's formula, because we thought that, okay, if this has certain generalization which is an entire function of s, that would give us analytic continuation in C minus 1 at once for our zeta function. Unfortunately, that isn't true. Here is our generalization of Hermite's formula for our zeta function. As you can see, the single integral in the previous formula is now generalized to a triple integral, again involving all elementary functions. But this particular one is analytic only when real s is between minus 1 and 2. So here is one of our main results. Actually, it consumed about 6 pages of the paper because one had to very carefully and painstakingly go from one integral to the double integral to the triple integral and try to prove the analyticity. But it is only analytic in this region, minus 1 less than real s less than 2. And so if I go back, if this is analytic in real s between minus 1 and 2, and I see a simple pole at s is equal to 1, what I could do is, if I have first obtained this result for real s between 1 and 2, see, this is the usual series definition of the zeta sub w. The right-hand side is giving it another representation valid in this region, but now I've proved for you or told you that this is analytic in extended, it is analytic in minus 1 and 2. So I could use this as the definition of zeta sub w in between minus 1, when real part of s is between minus 1 and 1, of course, s not equal to 1. So that is analytically continuing zeta sub w by means of this result to the left of the right half plane, real s greater than 1, up to real s greater than minus 1. So as I said, I'm not going to go over the proof of this at all, but I just wanted to say that one crucial asymptotic that one needs here is an asymptotic for this integral, which I had developed previously with Professor Zaharescu and Arindam Roy. Okay, so this slide I already explained. So the thing is, this identity is first true for real s between 1 and 2, but this is analytic in minus 1 and minus 1 less than real s less than 2. So I use this right-hand side to define zeta sub ws comma a in this extra region. And then just because I have defined it to be zeta ws comma a to be equal to this, and because this right-hand side actually reduces to the right-hand side of Hermite's formula when w tends to 0, I get this result, that even in this extended region, the zeta sub w reduces to Hermite's zeta function when w tends to 0. I would just wanted to say that this minus this was our definition of the phi sub w in the modular relation. And as you can see, one has absolute convergence when one constructs infinite series of this minus this minus this because of this big O bound. What I'm talking about is when I consider a series of this function where I have that minus the first two terms, I do get an absolutely convergent series. And so the explanation of this particular term is that it's a generalized Hurwitz-Zeta function defined by an absolutely convergent series for real s greater than 1, and by means of this Hermite generalization in between -1 and -1 less than real s less than or equal to 1, s not equal to 1. Okay, of course, when one generalizes things, then to show that one gets to the base case is often a trivial case, but in this particular case, it wasn't. To show that this triple integral, as you can see, there is no w now. So I'm letting w be equal to 0, or you can say limit w tends to 0 here. To show that this triple integral reduces to a single integral, require this formula of Ramanujan, the modular type transformation, which I discussed in the very first slide. So it did involve some non-trivial applications of Ramanujan's results. I know I have maybe 5 to 6 minutes, so let me go quickly over some of the stuff and omit some other stuff. Let us consider now again zeta of s comma I, Hurwitz-Zeta function, and let us assume that real s is greater than 1. So I can use this nice series for Hurwitz-Zeta function, and let me separate the first term n equal to 0, so which is 1 upon a to the s, and so I have essentially again, if I replace n by n plus 1, I'm back to n equal to 0 of this, which again becomes Hurwitz-Zeta function. So very simple relation between zeta of s comma a plus 1 and zeta of s comma a. So of course, one wants to try to see what one could get for this general zeta function. Unfortunately, all of our attempts to getting a relation for this difference or expression for this difference have proved to be unsuccessful so far. One reason why this looks to be a tough problem is because you see here how easily the a parameter was here. In the case of Riemann zeta function, you had just n. Now you translate it to n plus a. In the case of this particular zeta sub w s comma a, look where does a sit? A sits in here, inside the double integral, in the integrand of the double integral. So even if you replace a by a plus 1, it's very clear that things won't be as easy. Okay, I'm going to skip the proof of this, but I would want to just say what are the things that one needs to develop. So here are two kernels. We call them as first Koshlikov kernel and second Koshlikov kernel. So the first Koshlikov kernel is something that is very useful because it plays a role, instrumental role in Voronoi summation formula. Voronoi summation formula associated to sigma z of n. But the second one is what is useful in our case. So note the difference between this m function and L function. There is just a difference of having a plus sign here and a minus sign here. So one needs theory of functions phi and psi which are reciprocal in this kernel. And okay, let me skip this. Let me just show that this is one general result that one needs to first obtain. As you can see, this was the integral which occurred there, but this z was delta 2. Now this z is in terms of certain Mellin transforms, and one gets this particular representation for it. The specializations for this theta function, cap theta function that we are going to make reduces this to what one could call as a Lomel function generalization. But I would not go over it. But what I wanted to say is that a lot of things have their generalizations in this W parameter. So I'll skip the convergence of this series. But let me only tell you that I'm talking about functions which are reciprocal in this particular kernel. How do I know that such functions exist? What if that set of pairs of such reciprocal functions is an empty set. Well, Koshlikov has obtained for us a very beautiful result of a function which is self-reciprocal, not just reciprocal, a self-reciprocal in this kernel. So when you integrate t times the k Bessel function in this against this kernel, you get back the same thing, x times kz of x. So already there is one member in that set of pairs of functions which are reciprocal, namely t times kz and t times kz. What we needed was a generalization of that. So this function, I'll define what this 1 kzw is. But this function is what you get when you integrate the second one against this kernel. And when you integrate the first one, namely this one, against this kernel, you get back what you had here. So that's why these are called as reciprocal functions. And when we put w equal to 0, one gets Koshlikov's result. So in just 2 minutes, I'll stop. I just wanted to say that the function that we saw on the previous slide is a generalization of the modified Bessel function, a new generalization of the modified Bessel function. So it is in terms of this inverse Snelling transform representation. So if w was equal to 0, then this would have just reduced to x times kz of x. But now one has this general w in here. And why did I suddenly move into reciprocal functions in second Koshlikov kernel or this generalized modified Bessel functions is because both these theories of the reciprocal theory as well as the theory of this function are required to obtain our modular relation. And I think before I discuss two more slides, I would want to just say that this was one new function that we have encountered in our paper. This was the other one defined on the previous slide. Are they connected? The answer is yes, they are connected through this relation. And in order to prove that, one actually generalizes Ramanujan's formula that I had on the first slide. So you know when w equal to 0, you know the formula for the integral analog of Jacobi theta function. So we have a generalization of that, and that plays a role in getting the relation between these two functions. Hurwitz's formula, we tried to get, we could not. If one gets that, then probably one can go beyond real s greater than -1 and analytically continue. But all of our attempts for the past 6 months were unsuccessful. Okay, so let me conclude by saying that we have just initiated this theory. A lot of results are still to be developed. For example, again, the basic question on whether one can analytically continue or whether there exists analytic continuation of this generalized Hurwitz zeta function to the left of real s greater than -1, so that one can say it has analytic continuation to c -1. In w equal to 0, because it reduces to Hurwitz zeta function, we of course know that is the case, that one can analytically continue in c -1. But for w non-zero, we don't know. We encountered psi sub w of a, but not generalized gamma function, gamma sub w of a. Perhaps one way would be to try to obtain generalization of Lerch's result, where one starts with Hurwitz zeta function, differentiates it, put s is equal to 0, and then gets gamma. So in this case, we would replace it by zeta sub w. My student Rahul already has some results in this regard. However, we did not put it in this paper. We got it after this was submitted. The last one I don't even want to say. It's too far fetched right now. So I'll end with this quote by George Andrews and Bruce Byrne. They say in the preface of 4th volume on the Lost Notebook that one of the hallmarks of Ramanujan's mathematics is that it frequently generates further interesting mathematics, and this formula is no exception. What is the formula that they are talking about? That's the formula on page 220 of the Lost Notebook, the one which was discussed in the very beginning of this lecture. With that, I'll stop. Thank you very much.
Thank you.
Yeah, please let's thank the speaker for
Thank you. If there are any questions, I may be happy to answer.
So I had a question.
Okay.
You said Hurwitz formula, you call it. Functional equation or whatever you would like to call it.
Okay.
So it comes from, I mean, the standard would be you make it into some sort of contour integral and go from the real axis to the imaginary.
That's actually a good way. We haven't tried that, though we have pondered upon it. So, right, one actually takes a loop coming from minus infinity, circulating around the origin, and then going back to minus infinity. That did play a significant role in Hurwitz zeta function. Hurwitz himself actually used it to get analytic continuation in C minus 1. In our case, though, because the basic definition looks to be somewhat more involved, this might be somewhat more difficult. But yeah, that is one way to try to get analytic continuation. Try to see if one can analytically continue in C minus 1. But let me say that we tried to generalize Hurwitz formula. Things become very difficult with regards to asymptotic nature of certain functions. We haven't been able to say that, okay, there is no Hurwitz type formula for zeta of s comma a or a functional equation, but we haven't been successful so far in getting it.
Okay, thanks. That answers my question.
Thanks.
Any other questions?
Hello.
Yes.
Hi, Atul. Siddhi here.
Hi, Siddhi.
Thank you for the nice talk. It was very interesting to see the generalizations. I wanted to ask if the value at 0 in your integral seems to be special. Have you been able to look at the value at 0?
So 0 mean W equal to 0, you mean?
No, sorry. I meant S is equal to 0.
Yeah, S is equal to 0, we have actually computed the value. So
okay.
I did not put it here. So if you have zeta of 0 comma a, the Hurwitz zeta function at S is equal to 0 is simply 1 half minus a.
Yes, that's right.
So when a is equal to 1, you get just zeta of 0 as minus half, which is well known.
Right.
So in our case, it involves error functions, which all reduce to 1 and giving you 1 half minus a actually. But that is another important thing. One, if we are able to get analytic continuation in C minus 1, the next question would be to try to see what special values of
at
this
negative
zeta sub w at negative integers. Or, yeah, I mean, at odd zeta values, I think it's too far-fetched at this point of time. But at least at negative integers might be the next easiest thing to do, provided one has analytic continuation. Yeah.
Right. No, I thought it was interesting because you would get an equality with the value at 0 and the value at 2, right? Because you have this zeta of a
true,
and minus, 2 minus a, that kind of symbol.
That's true. But that is true only when real a is greater than 1. So,
okay.
Yeah. For real a less than 1, sorry. Maybe
yeah.
No. There is a symmetry along real a equal to 1. But
right.
So let me just show here. Yeah. So this zeta of s comma a, zeta sub w s comma a. Sorry. Yeah, here. Zeta sub w s comma a. So when I put s is equal to 0 with the analytic continuation, yes, you are right. Yeah, we will get this symmetry. Yeah. Okay.
Yeah. So I thought that would be interesting.
Yes. Yeah. Right.
Okay, thank you so much, Atul.
Yep. Thanks, Siddhi.
Okay, any further questions?
I just want to say that it was a nice talk and thank you, Atul.
Thank you, Professor Riddhi. Yeah.
Okay, I'm a physicist actually, not far less a number theorist. It was a very nice talk, although it was a bit too fast for me. Is it possible to share your slides through these email?
Sure, sure.
Gaurav, could you
Yes.
do
Yeah.
that?
Yeah, I'll share it to Gaurav.
We can just make a link on our website, and then I'll send you the link.
Okay.
Sure.
One question is that
Yeah.
you have these formulas which are sort of like one has for normal to check orthogonality condition for special functions of various kinds. Like you have some function phi or f and f star, and together with some prefactors, which in your case were in some cases gamma, and then I didn't quite, I don't remember exactly. Were those integrals evaluated exactly, or you had the answer for some of these integrals?
So in the definition of this,
The one that just went in the previous slide, the one probably before that, one slide. Yes, the one on top. For example, this Ramanujan's paper is a Hardy. This
yes.
one.
So this has evaluation, but it's an evaluation in terms of either an infinite series or another integral, infinite integral, that sort of thing.
Yeah, actually more like the second one, where it looks like if I ignore the cos factor, which I don't understand now, but this would be sort of a normalization condition for the cap C function, right? With some measure which is dependent on these gammas.
Okay. Okay. So you are saying approximating this C function with C star or something of that sort?
No. This formula itself, the
Yes.
second bullet point about this integral that you have here.
Yes.
This one looks like mod square of some function, and that's the kind of thing that comes in when you want to check for orthogonality. Although here there is only one function, but suppose we had different functions of this kind. Do you have generalizations for this for Dirichlet L functions type functions also?
Yes, I have generalized this for Dirichlet L functions, but beyond that, not for other ones. For example, one interesting thing would be to see the cap C function associated with the Dirichlet series for Ramanujan tau function. So then try to get integral representations of this kind and work with them. That or more general Dirichlet series also. So I don't know about more general ones, but for Dirichlet L functions, I did obtain.
And these are given by some sort of complicated infinite series.
Yes.
The answer.
Yes. Right.
Thanks.
So one other point that I wanted to make, and here is where physics might play a role, is in the definition of this generalized Hurwitz zeta function. This extra parameter now is W. So it plays a role for getting generalizations of many special functions, well-known special functions. But we don't know what really this deformation parameter W is meaning. Let's say in the theory of modular forms, or where in physics one might encounter this. It seems to be some very natural thing, because the theory that gets developed from here is, one has nice properties and rich theory coming out of this. But since we approached it through this question of whether we can put theta structure on it, we haven't been able, or we are not even competent to try to see what the perspective of physics would be in this regard. So one question would be to try to see what the role this W, this deformation parameter W, plays in other areas.
Mhm. Could you explain what is the theta structure? I mean, you explained that during the talk, but it was probably a little too
Yeah.
fast for.
Okay. So the theta structure, by theta structure, I meant that you have, let's say, this general modular relation, and now you want to put an extra parameter w, which makes that generalized function transform in this way. So it will be equal to itself with w. I mean, it will be invariant only when w is replaced by iw, and simultaneously alpha is replaced by 1 by alpha.
I see.
And the reason why I call this as a theta structure is because the prototypical example is the Jacobi theta function and the theta transformation.
Uh-huh. Okay. Thanks.
Thank you.
Hello.
Yes?
Can I ask a question?
Sure, sure. Please.
Now you see, you take Bessel function, then Jx, Jy is integral of Jz with respect to a measure which is concentrated on mod x minus y2 x plus y. And in harmonic analysis, we say that this gives rise to a hypergroup structure. So when you had those triple integrals, you
Right.
know, these could be coming from products or things like that. Like all orthogonal polynomials, when you multiply P and Pm, it is summation from mod n minus m to n plus m. When you take Pnx, Pny, then it is
Yeah.
integral of Pnz with respect to a measure concentrated on mod x minus y to x plus y. And that gives rise to various polynomial hypergroups. And from hypergeometric functions also, various hypergroups come. So when you had that triple integral,
Yeah.
that thing was working in my mind. It is because of that integral, because of products, because why Fourier series work fine, because EIMX is simply EIN plus MX, and
Yes.
EINX EINY is simply EIN x plus y. So there it is, that measure is concentrated at single point. But when you expand in terms of polynomials weighted by e raised to minus something to make integral, then when you take products, these integrals do enter, but we do have nice representations. So all that comes under the theory of orthogonal polynomial hypergroups. And since you used Bessel function, I started with Bessel function, and it comes from rotation invariant functions. You take rotation invariant functions on R2, and you multiply, you convolve to rotation invariant point measures that is concentrated on circle of radius R and circle of radius S. When you take the convolution, then it is integral with respect to a certain measure from mod R minus S to R plus S. So can you explain those three integrals via this kind of argument? That is what I wondered, one thing.
Oh.
Okay. And
Yeah.
secondly, it would be good if you number your slides, then we can go back and forth to the slides that we want to go back to. We can always remember numbers well rather than the whole page. That is
Okay. Sure. Sure.
okay.
I'll keep that
So
in mind.
it was very interesting talk. Third
Thank you.
thing that I want to say is, that Dustermuth has very nice for account of Jacobi theta function. He was a great expositor also. His Berkeley talk is very good. So you are avoiding the function z going to z plus 1 all along. But
Yes.
Riemann had another important function which is called Riemann function, sigma sine n square 2 pi x divided by n square, which is uniformly continuous, but it is not differentiable.
Nowhere differentiable.
Hardy and Little would prove that it is not differentiable at irrationals and also at not certain rationals. And an undergraduate, John Gerber, proved that it is not differentiable exactly at the leftover points. So I made my student write MPhil dissertation on that, and I heard this from HP Dixit, another Dixit, his talk. Okay, so I wanted to point out that relation and his associate Parajita. So I mean, are you giving any attention to the other invariance Z going to Z plus 1, or you are avoiding that altogether?
So this question has been in my mind since many years now, how to incorporate Z going into Z plus 1, because then that particular integral or whatever function will get, that will be a modular form, and then there is a whole theory of modular form at our disposal. Yes. Unfortunately, if you see how that Z going into minus 1 by Z, or equivalently alpha going into 1 by alpha is placed, it's inside the argument of that cosine function, and there I tried to see how to incorporate this other translation, and so far I haven't been successful.
Okay, because that gives rise to wavelet representation, because there are two transformations working, Z going to 1 by Z and Z going to Z plus 1. That is what Dustermert's nice article explains very well and applies it to Riemann function that I told about. So and wavelets are popular these days, even. Okay. Fine then. Thank you. Very good talk. Thank you.
Thank you, ma'am.
Okay, then Gaurav.
Yeah, so it's a real pleasure to actually not only have Atul but also Dr. Ajit Iqbal Singh in a talk in Delhi. I know she hasn't been feeling too well to travel for all the talks, but she was always there to encourage all of us. So it's Atul, you're lucky that ma'am is here, because we are.
Thank you very much, ma'am.
No, I was the learner in the process. Thank you. I learned in the process.
So I remember meeting you at the Delhi conference again in 2012.
Oh, okay. Oh,
Yeah.
Good memories. Yes. Okay. Thank you. We must get together. Okay.
Sure.
Yeah, if you like, I can send you some of the references, because you do have that triple integral and Bessel function. It is in section 9 of paper by R.I. Jewett in Advances Maths 18, volume 18, 1975. So this is explained very well,
Sure. I'll take a look at it. Thank you.
Okay, so thank you very much, everybody. I think many people have now left, but some are all there. We will again have another seminar in another 2 weeks, hopefully, and this looks to be a very, very interesting start.
So before we close, let me remind that at 6 o'clock, Ken Ono is giving a talk on a Zoom meeting. So in case anyone wants to attend, I can share the link to Gaurav. So Ken Ono is giving a talk on why Ramanujan, the man who knew infinity, still matters. That's the title of his talk.
Relevant.
Yeah, so is there a link?
Yes. I'll forward you the email. And,
is it not that Vigyan Prasar series?
Yes.
Yeah.
The Vigyan Prasar.
Yes. And many of them have link, because when Dinesh Singh gave a talk, then I sent the link to many people.
Maybe I would like a link of that.
Okay. Sure. So Gaurav, can I forward it to you so you can send it to everyone?
Yes. Forward it. I'll just send it to the whole.
Okay.
Thank you. So thank you, everybody. See you in 2 weeks, I guess.
Yeah. Thanks a lot, Atul. Bye.
Thanks, Krishna.
Thank you, Gaurav.
You had some questions, Fatima?
No, I was just thinking Atul for the talk.
Okay.
Thank you. Yeah. Okay.
See you guys.
Okay, see you sometime. Bye.
Yeah. Thanks, Gaurav.
Bye.
Bye.
See you, Riddhi.